before we can move to something like the Heisenberg uncertainty principle. Let's see how we are going to transform from one basis to another. Okay? So we did this in a very abstract fashion yesterday. Let's give a concrete vision of this. So what we'll begin with is to ask ourselves that if I give you the momentum operator in the position representation, that is something you're familiar with from your first course. That the momentum operator is related to the differential. Good. Now if we use this, and let's say we act on some general state alpha. Alright? Now since we already represented the momentum operator in the position representation, if we want to know what is the outcome of this object acting on some general state alpha, then it's smart to also transform the state alpha into a basis in which this momentum operator could naturally act. Okay? So there are two choices you could go with. One would be that you could write alpha very directly in terms of the momentum eigenfunctions. But for a moment, I want to take you through a slight roundabout. Because I've written the momentum in the position representation, why not also write the state alpha in the position representation? Okay. So this we went through yesterday. So this state alpha I'm representing in terms of the complete set of states in the position representation. And since that's a continuous basis, I've used an integral here. Okay. So this ket bra in x integrated over all x, that's the complete set of states. I've sandwiched that in between. That's just the identity operator. I'm allowed to do this. This allows me to transform alpha, the ket alpha, some general state, into the real space representation. As a consequence, this object, this probability amplitude of projecting the state alpha onto the position eigenfunction, on the position eigenstates, gives rise to these eigenfunctions, okay, of alpha in the real space basis, psi alpha as a function of the variable x. Okay. And now note, P can act directly on these eigenkets x, which is what I wanted because position was represented in terms of the real space coordinate x. It was written in terms of the real space derivative dx. Okay. So then acting with P on alpha has left me with this. Okay. But you can see that the momentum operator acting on this wave function psi of alpha essentially means you're going to be doing this. This differential operator with the minus IH cross is going to be acting on that, the probability amplitude, okay, of alpha ket bra x. Okay. So now, if I take this state, take the left hand side, right hand side, and also take bra x, sandwich it, the bra x from the other side, alright, then that bra x and this ket x, they will just happily, do an inner product. The integral will take care of everything and it just becomes 1. And all we're left with is the thing inside the brackets above. So essentially, if I take that, the action of P acting on the state alpha, and if I want to know how much of that is weight, how much is the weight of that action on some eigenket x, then that's what sandwiching with this bra x does. And that just gives you that the stuff inside the bracket minus IH bar delta x acting on that wave function psi alpha of x. Okay, that's the weight factor. Alright. Okay. Sorry? Yeah, so what that bra is doing, okay, is asking that you acted with the momentum operator on some general state alpha. right? But the general state alpha was written in terms of all the eigenkets in X, right? Now I just want to know how much is the weight factor for some particular X. So then I've taken that particular X as from the bra space, and I'm taking its inner product with this guy. So it just pulls out one particular weight factor. Got it? Good. In general, if I hadn't worked with some general state alpha, if I'd repeated this entire story right from the beginning with some state X itself, and then taken X prime, then this entire set of steps would have just led to this, a derivative acting on a delta function. You can verify this. Carry out the algebra for yourself and check this out. But let me instead tell you that if I take this P acting on state alpha, and I know what it looks like, now instead of seeing how much is the weight factor along some eigenkate X, instead I ask, okay, what is the weight that this has with some other general state beta? Then I take that beta from the bra space and take the projection onto that. Okay, so this is that matrix element. So now the operator P is between two very general states, alpha and beta. Okay. Then this beta, the bra, that's going to act on the state ket X and give you this weight factor. Alright? And this weight factor can be written as psi beta X but complex conjugated, star. Alright? And then of course you have this weight factor where the momentum operator acts on psi alpha of X. So this is telling us how very generally we can carry out calculations of this kind. Let's say you're working, so I've given you here a particular example where I chose to represent the momentum operator in the position representation. Then I rewrote some general state in the position representation, acted with this operator, the momentum operator on that state, okay, very generally, and then I even saw what its overlap with some other general state beta looks like. Okay. So in a step-by-step fashion, you can see how it looks. And indeed, if you think carefully, expressions of this kind, this entire thing here, you've actually seen this in the past. If I were to tell you that, okay, so let's think about the following. Take the harmonic oscillator. Are the wave functions you derived there for the Hamiltonian, the energy eigenkets, were they also eigenfunctions of the momentum? Were they? Can somebody tell me? Were they eigenfunctions of the momentum? Yes or no? No. Why no? Those states were actually eigenfunctions of something else. Those ladder operators, A and A dagger. And A and A dagger were actually linear combinations of X and P. Okay? So therefore, by construction, they could not have been eigenfunctions of just P or just X. Okay? So now the question is, since those states were not eigenfunctions of the momentum, if I act with the momentum on one of those states, what will it do? Can you guess? I'm sorry? Suppose I take one of those eigenfunctions, the ground state, and act with the momentum on that. What will it do? It will lead to a mixture of states, right? Because it's not, in general, acting on its eigenfunctions. So now the point is, if I were to ask you, so since it acts on a mixture of states, this mixture would also include some of the other excited states as well. Why not? In general, it would be. It would take you into all the other possible states. Which means that such matrix elements, where alpha, let's say, is the ground state, and beta is some other excited state of the harmonic oscillator, that would make sense. Maybe you never computed this in that problem. But if you had, you would have received non-zero answers. Now think back to that first course. What was the recipe your instructor told you? When you compute expectation values like this, you take that operator, sandwich it, so this was the operator, I h bar delta x, put it between one eigenfunction, put it with the complex conjugate of the other eigenfunction, integrate over all space. But that's what we've got here. Okay. So this is how we make sense of what's happening here. Okay. Now to make this more concrete, let's ask ourselves, okay, let's take a momentum eigenstate. So far we've been doing something, rather brutal. We were working with non-eigenstates of the momentum. We were purposely working with the position eigenstates. Those are actually not the momentum eigenstates. Certainly not. And by the Heisenberg uncertainty principle, there's a huge problem in working with them. But now let me assume that the operator acts on its own eigenstates. We know we get eigenvalues. Good. Now suppose I want to check how much is the weight factor of the action of this eigenvalue equation, P operator acting on its own eigenstate, but on an X eigenvalue. I can ask that also. Right? I can flip the game around. Let's say it initially acts on its own eigenstate, gets you an eigenvalue. But now I purposely want to ask, what is the weight factor of this with some eigenket, but from the opposite representation, the real space representation, X. Then that would give rise to something that looks like this. Alright? Now think. Why would we get this? Can anyone tell me why would we get this? Right, in the real space representation. Okay, and then? Okay, and so? Why am I allowed to switch the two? Right, so I've used the chain rule to apply, and then what happened to the other term?
Del by del x of x bar is 0.
So there will be another term in general, and that term, by the integration by parts, must have vanished, giving rise to only this. Okay. But at the same time, I can also say that P operator acting on P gives rise to an eigenvalue, call it small p, and that will just filter out. So this guy will also be equal to this, right? With the eigenvalue just sitting on the outside, and you have this overlap between an x state and a p state. And that's this fellow. That's the momentum operator acting on this object. So now if you solve this, think of this as a differential equation. You can solve it. In fact, the simplest way to solve it is to guess a trial function. And believe me, the trial function is just this simple. Just take e to the ip x by h bar, of course with some normalization. And indeed, if you plug it in, you'll see it works. It gives rise to equation 5.89. It satisfies that equation. Okay. How would you get that normalization? Well, you know that the overlap between x prime and x is a delta function. Okay. So take that, okay, and within that inner product, put in a complete set of states of the momentum basis. That's this guy. Put that in the middle. That's an identity operator. You can do that. This immediately gives you these two objects, this fellow and this guy. But we already saw what that looks like. Okay. What that looks like is one of them will give you e to the ipx by h bar, the other one will give you e to the minus ipx prime by h bar. So that gives you this phase factor with an integral, and you'll have this mod square. Okay. Why the mod square? Because one gives you n, the other one must give you n star. Good. And this guy is actually equal to 2 pi h bar times the modulus n square into the Dirac delta function. How do I know that? It's because by definition, this is one form of the Dirac delta equation. This integral minus infinity to infinity dp of this phase factor is equal to basically 2 pi h bar, if I just take that over here, into this delta function. That's a definition. Okay. What is the physical meaning of this representation of the Dirac delta function? It basically means that if I take a lot of different waves Think of these e to the I px by h bar like objects as waves. Okay. I take all infinite members of those waves. Each member is tagged by p, the index p. Alright? And I take all of them and I sum over them. Here it's an integral because the p is a continuous variable. So I sum their contributions, divide by this 2 pi h bar, and it just looks like that peak. Okay? This function is extremely sharp. When x is equal to x prime, poof, it goes bang. And as soon as you step away, when x prime is not equal to x, it just collapses to 0. Alright? So, one way of actually visualizing this is something that we described in an earlier class, where I said that look, you can actually localize a particle at some point in space, okay, by adding up a huge number of waves. That's exactly this Dirac delta function. Because this Dirac delta function tells you that when x prime is equal to x, you have something sitting there. Okay, that function is just about a blip, and it's 0 everywhere else. Which means that if this kind of object describes the wave function, the state function of a system, then the particle would be sitting right there and nowhere else when x prime is equal to x. And how did I do this? I had to add up an infinite number of waves, okay, add up all their contributions, and then I got this. Yeah. So x prime, let's say, would be my operator, measurement device, right? And x would be the real position of that particle. When they coincide, I see the particle sitting there. If they don't coincide, I don't see the particle sitting there. So using this definition of the Dirac delta function, I find that the normalization is just 1 by 2 pi h bar square root. Okay? So this tells me that this object, this overlap between x and p, look at it, it's actually non-zero. In an earlier class, some of you would ask me that such overlaps, these probability amplitudes, should they just be numbers? And I pointed out, look, they can be numbers, but in general they're functions. Look at what kind of object this is. It's a function, e to the I px by h bar. But it's also got a number associated with it. That weight factor is 1 by square root of 2 pi h bar. Okay. So in general, the overlap between such objects, one from the Ket space, one from the brass space, will give rise to functions, not necessarily numbers. Here we call this a transformation function. And there's a reason we call it the transformation function. This object will actually help us go between real space representations of wave functions and momentum space representation of wave functions. Okay? That's why we call it a transformation function. You can use it literally to go from one description of a system, let's say real space description of a system, and a momentum space description of a system. What does this mean classically? What it means classically is, let's say you're working on some problem, and you know how to describe every constituent of that problem in terms of the real space coordinates of those constituents. You know that very well. So that would be like a real space description of that system. But let's say you didn't know how to describe it in terms of the momentum. Okay? But conversely, a friend of yours says, you know what, I know how to describe all those constituents of the same system in terms of their momentum, but I don't know how to do it in terms of their positions. Now, how would you compare with you and your friend? You have a description. This friend has a description. How would you match them? Surely, the objective reality of the system should be independent of your descriptions. Right? So you should be able to go between them. The miracle of the classical world is that, and this is a miracle, that any observer in the classical world actually has a complete description of both momentum and position at the same time. It's always available to us. In the classical world, in the quantum world, the bummer is that you have a separation. If an observer has an extremely good representation of a system in the position basis, their description in the momentum basis begins to look really fuzzy, and vice versa. So this is a headache in the quantum system. Okay? it's a headache if you think of it from the classical point of view. It's actually the physics of the quantum world. And we have to know how to appreciate it and exploit it. But that's the way it is. Okay? So this transformation function now will allow us to do the following. So to start with this object. Some general state alpha, okay, which I am representing in the real space. Okay. So this is my psi of alpha x. Okay. So this is a real space wave function. I can always choose to write this in terms of the momentum basis, right? So I sandwich that complete set of states. I do that trick, and I know that this xp now, this looks like this e to the ipx by h bar with this weight factor. And this p of alpha is psi alpha of p. I know that too. Okay, good. So what is this telling us? This is telling us, look at this object. This is a recipe that tells you that if you gave me all these psi alphas of p, so if you gave me a complete description of the system in the momentum basis, how to reconstruct a position description from it. Because what's sitting on the left hand side is a position space representation. Psi alpha is a function of x. What's inside the integral on the right hand side? P. So this in the quantum world is telling you how to get these two friends who have these different descriptions to start comparing with one another. Okay, so that's the recipe. You give me your momentum space wave functions, I'll multiply it by these phase factors, do the integral, and bingo, I should be able to correlate it with my answers. Okay. I can also do the opposite. Suppose I took P with alpha. Alright, so this guy is actually psi alpha of P. Now here, I put in a complete set of states in the position representation. Get bra, x, okay, with an integral over all x. Then immediately, what I get out here is that I get wave functions in the position representation with some phase factors e to the minus I px by h bar, and then I do the integral over all space. So again, this is telling me that I can also do the opposite. That if I have all the real space representations and my friend has a momentum space, I give this friend of mine all of my wave functions and say, okay, multiplied by these phase factors, integrate, you should be able to compare with your answers. Okay. So this is a recipe to go back and forth. Note, I have established for you that this is a two-way street. This is not a one-way street. It's not as if I can only go from position space to momentum. I can also do the converse. There is a nicety here. The nicety is that the way I will do this transformation, in one case uses e to the ipx by h bar. In the other case it uses e to the minus ipx by h bar. Okay? In one case it's an integral over all momenta, in the other case it's an integral over all space. And indeed, these things go by a name, these transformations. They're called Fourier transformations. Alright? So the mathematicians, people like Fourier, actually realized how to do this in harmonic analysis way before quantum mechanics was ever invented. So the people who are inventing quantum mechanics or figuring out this language, they already knew how to fall back on a lot of this technology. It had already been developed by the mathematicians, way before them. Okay? So this is quite amazing. And you can see, so, yeah?
So regarding this transformation, how come this not violate the uncertainty?
No. That's a very good question he's asked. He's saying, how come this doesn't violate the uncertainty principle? No, my friend. Actually, this is the uncertainty principle in action. And that's what I was going to say next. So thank you for anticipating what I was going to say. Look at how we've carried out this magic. This is not a one-to-one transformation. So it's not as if I've taken one real space wave function and constructed one momentum space wave function from them. No, in principle, I have come all the momentum state wave functions. I multiply them by their phase factors, respective phase factors, add up all the contributions, and then I get a single real space wave function. And vice versa. I have to take all the real space guys, multiply them by the phase factors, add up all of them, and I get one momentum space wave function. Okay? So what this means is that I actually need a huge number of one guy, of one set, in order to construct one member of the other, and vice versa. So what is this telling you? That in this quantum world, if I think of the real space basis and the momentum space basis, every one member of one of the bases is talking to every one of the other guys, and vice versa. Think about that. That's what this guy is actually telling you. It's not a straightforward one-to-one recipe. It's many-to-one and many-to-one on both sides. Okay? That actually is the Heisenberg uncertainty principle in action. Because if it had been one-to-one, that would have been like the classical one. Actually, it's not like that at all in the quantum world. Okay? Good. Alright. A slightly more sophisticated way of thinking about this. Transformations. Why do we do this? It's because, again, I'm going to set up a language here, which we're going to use later in the course, where we're studying symmetries. Okay? So this language that we're going to set up here is going to be very important for us going forward. So please pay attention. When we were doing a change of basis, what were we doing? Okay? So certainly you can say, we're doing a Fourier transformation. That's right. Okay? But there's another way to think about this. This change of basis is nothing more than a rotation, if you wish. Okay? It's a rotation. Like for instance, I might have used this example with in a class which I taught you a couple of years ago, in electricity and magnetism, that if, let's say, you do your experiments in a laboratory with an axis frame like this, and your friend, for some reason, does it with a reference frame which looks like this. The answers cannot be different between the two of them, but they're going to look different. How do we reconcile this? Well, the answer is simple. The two of you should sit together and realize, wait a moment, I should be able to translate all your answers through a simple rotation and get back to my answers. There should be a straightforward recipe to go from A to B. Okay? It might be somewhat complicated, but it's possible. In the same way, when I went from the real space wave functions to the momentum space wave functions and vice versa, this was a generalized notion of the same rotation. I'm taking one complete set of states, written in some basis. I'm just translating it into another. This so-called translation is just a set of rotations of that space. Okay? Now the way I would do this, go from the old ones into the new ones, is that I would use some operator to do it. Think of these rotations as themselves being some operations. Why? We know that when some operator A, acts on a state psi, in general it goes to psi prime. This is the most general rule of any operator, right? So here, I want some special class of operators. Can anyone tell me what is special about this? Tell me what is special about these operators that I'm looking for. That's right. Well done. So, if I rotate my fingers from here to here, the lengths of my fingers didn't change in doing that. It's not as if, like Pinocchio's nose all of a sudden it started stretching or shrinking. That didn't happen. It was just a simple rotation. So, which means that in this language, the norms, the lengths of various vectors, they have to stay conserved. They must stay fixed during this transformation process. Okay? Because if that changes, then all hell is going to break loose. Because then when I compare answers, I will also have to keep track of that change as well. So you want to eliminate that possibility. That you have to remember. When we make these transformations, in order to compare answers very quickly, at least you have to make sure that the lengths of these vectors remain the same. Like what you call I cap and what I call I cap. You call yours a unit vector, I call mine a unit vector. It's a unit. Right? It's just that yours looks a little wonky to me, mine looks a little wonky to you. But they're still unit vectors. That property has to be on board. So therefore, we use something called unitary operators. Okay, and we'll see why these are so important. So these unitary operators, okay, just think of it as following. If they act on some state, we want to go from a basis of size to a basis of phi's. So I take psi1, act with it on this operator u theta, take it to phi1, etc., etc. I act consistently on all of them, all the size 1 to n. I go to phi 1 to n. Okay. Now this operator, okay, we use a particular language. If you've never heard this language before, pay attention. We say that this theta, you know the index there for the u, we say that that theta refers to an operator that acts as the generator of the transformation. Okay. So for instance, you can ask the following. If I'm going from here to here, it's a rotation. How do you quantify this? You say, well, you know, I have certain angles, and then some of them are changing by so much, some of the others are changing by so much. So you will give me numbers, right? So even here, there must be a way to quantify all of these rotations, right? And you will also say that the act of rotation itself was important. In the quantum world, who will do that rotation? Some operator has to do it. Okay. So in these unitaries, we have some operator sitting there, and they will carry out the rotation by certain amount. 90 degrees, 600 degrees, I don't know, whatever, but by some amount, they have to do it. Okay. So that's why we write down these u of theta in a very particular way. Look very carefully at that structure. There's a method to that madness. It looks like u of theta looks like e to the minus I epsilon theta by h bar. Let's go back above and now let's compare it to this fellow. E to the minus I px by h bar. Look at that guy. The operator there was p. Okay. The amount by which I was doing the transformation was x. Alright. In the same way, here I use some operator theta. And what is the quantifier of the rotation? Epsilon. Some epsilon. The h bar is a telltale sign that these transformations are happening not in the classical world but in the quantum world. Okay? So if in your unitary operators h bar is not hanging around, you should tell me why.
That you have defined it as a matrix exponential.
In general, it's a matrix exponential because operators are matrices.
But why would we expect that the space of all our unitary operators will have, say, only one generator? We're trying to have
No, they can have multiple. I'm trying to motivate the thing, so I'm starting with simplicity. Do you like to jump into the most complex thing right in the beginning, Fabio?
No, but why would we expect it to have a generator?
Oh, well, in the quantum world, any action is the outcome of the operation of some operator on some state. Yes or no? So in that case, it's sensible for me to think that this unitary transformation is going to be the outcome of some operator acting on some state. Now, how do I write down that operator? I'm showing you a recipe.
But can't we have subspace that that particular operator we have written down we cannot reach?
In principle, yes. But कहीं तो transformation करना है आपको भैया. क्या वो भी आप allow नहीं करेंगे? Somewhere we have to proceed, no? So I have to have some set of states. I will act on them, I will transform them, yes or no? Okay, good. So therefore my claim is that these operators do a great job. And I'll prove to you that these operators preserve the norms even as they do their job. Okay. How do I motivate some of this? Think of these objects as phases, if you wish. Why? Because when they act on a state, if I take the basis of states on which they are acting, such an operator, if these are eigenfunctions of theta, then they will pull out eigenvalues. Yes or no? Look at this. If theta operator acts on theta state, it gives me an eigenvalue theta. Yes or no? You agree with me on this? Good. Now if I take some function of theta and I act on this, what will it give me? The function of the theta eigenvalue. Does that make sense to you guys? Good. This of course is true as long as this function is analytic. If it has something kinky going on, we don't know. But let's not wrap our head around that, that stuff. Okay? Now, My claim is that these guys are very good. Why? Because if I have objects like this, if I have e to the I epsilon theta, where theta is not an operator, it's an eigenvalue. What is that? What do I call such an object? I call it a phase. Why? An exponential e to the minus I something. What is the unit of that something? Yes. What is the unit of that something? E to the I something. What would the unit of that be? Would it be length? It's dimensionless. We think of those as angles in general. Right? And e to the I theta can always be written in terms of, in a very simplistic manner, in terms of cosines and sines. Right? Well then, in that case, you would not be surprised that these guys are going to be the amount by which you actually carry out the rotations. And the cosines and the sines are just the weight factors associated with those rotations. Right? It's not rocket science. I mean, it's straightforward if you think about it. Okay? Now, why unitary operators? My claim is that I've taken the operator here. Now look at this operator. It's just got a phase. What is its amplitude? 1. It's just a phase. Okay? It's nothing but a phase. Its own amplitude is just 1. So the name unitary is not easy to spot. Its own weight factor is just 1, right? Yeah? So that is one way to justify where that word unit is coming from. Okay? But there's another way as well. Yeah?
You mentioned that the generator is
We're coming to that.
I will define unitary by the property U adjoint U is equal to 1 to the map.
That's right.
That's
It's coming there.
What the unitary is, or with starting with preserving probability in a product and then getting.
Sorry?
So when you say something as a unitary transfer, are we starting with the condition that it has preserved in a product?
Yeah, absolutely.
So is that the defining property, or is U adjoint?
No, I think okay, at least as far as the physicists are concerned, the defining property we'll start with is that they must preserve all inner products.
In math, we start with
I bow to them. But I insist that this is the way I'd like to communicate it. Because if I let go of this, right, I choose to start from here and I derive the fact that U dagger is equal to U inverse. Okay? So I want all inner products to be conserved. That was an obvious requirement. Good. And I also want that if U theta acts on psi, it takes me in general to some psi. That's a general thing that I want to do. Okay, good. So now let's look at some inner product. Let's take the inner product of some phi with psi. So this is the inner product of this guy with this guy. Something like this. Okay? Good. And I've done the rotation. And I've come to some new phi prime with psi prime. Sorry, my mistake. Suppose I had two operators, phi and psi, two vectors phi and psi in my rotated frame. I had their inner product. Now I look at it in the transformed frame and I want to look at their inner product. That's what I'm doing here. So phi and psi are in the old basis and these two are in the new basis, okay, or the primes. Now, using this rule that all the primes are related, all the new guys are related to the old guys through these unitary operators, the action of these unitary operators, you can show that this psi prime can be written as U theta acting on psi and phi prime is not U acting on phi bra. It must be U dagger because it's acting on the bra space. So this U dagger appears. Good. Now the claim is that if inner products are preserved, if this guy is equal to this guy, then the only thing that makes sense is that U dagger theta U theta must be equal to 1. Which means that U dagger theta is the inverse of U. Okay, that's a remarkable consequence. So this then mathematically defines the unitary operator. So I agree with the mathematicians there. I'm giving it the physicist's motivation. That for me it is all wholly that the inner products must be this thing, maintained. Okay. Now it turns out that in general, in quantum mechanics, these transformation operators come in two varieties. They can either be unitary or something called anti-unitary. Okay? Now what does anti-unitary mean? Well, Anti-unitary means an operator U whose action on some side, okay? If I have some C acting on the side, so there's some scalar. If the U acts on this, what I get out here is C star. Okay? That's what I call an anti-unitary operator. We'll come to an example of this later on. There's something called the time reversal transformation operation, and we'll see that that's not unitary, it's anti-unitary. But it turns out that that's probably one of the few anti-unitary transformations that we know of and use on a regular basis. So for the most of this course, we're going to be obsessed with unitary transformations. Alright? Now, it turns out that unitary transformations are intimately related to Hermitians. Okay? So the unitary transformation operator very generally can always be cooked up, can be formed from some corresponding Hermitian operator. So u of theta, when I was writing down u of theta, the theta there has a special property. It is self-adjoint. It is Hermitian. So its eigenvalues are always real. Let's go back to this example here. Did it occur to you that the P was Hermitian? It wasn't just any operator I was using there. P is a Hermitian operator. Okay, its eigenvalues are real value. Okay. In the same way, very generally, u of theta with some parameter lambda can be written as e to the minus I lambda theta, where lambda is real valued and theta is a Hermitian operator. That's very important. So here onwards, going forward, any time I tell you, oh, here is a Hermitian operator, you should be in your sleep be able to tell me, oh, I can use that to create a unitary transformation. Momentum, yes, e to the IPx by h bar. Hamiltonian, what would be the unitary operator for the Hamiltonian? The time evolution operator. In your first course in quantum mechanics, do you guys remember seeing this? It's the same beast as this e to the IPx, the same class. It turns out that this object is just what we call a translation operator. Why? Because it translates by a certain amount. And what does this guy do? E to the minus IHT by h bar? It translates but in time, not in real space. That's what we call dynamical evolution. We give it a fancy name, dynamical evolution. But essentially what this means is that we're just translating the system in time. But that means that the system has to have evolved. That's why we call it dynamical evolution. So this is also another unitary operator. So any time I give you a Hermitian operator, you should be able to tell me the corresponding unitary operator. What's the recipe? You should have guessed by now. What's the recipe? To figure out from a Hermitian operator how to get to the unitary operator. What's the recipe? E to the minus IPx by h bar, e to the IHT by h bar. What do I do? What am I supposed to do? No. What I mean is, how do you construct? What is the right way? Suppose I tell you, okay, here's some given Hermitian operator. How would you tell me, okay, this is the unitary operator that I can form out of this? So certainly the simple-minded thing is, yeah, I'll exponentiate it with a minus I and I'll put that operator. But now what? This operator, now what? That's right. So the point is you have to look for the other object, the amount by which the translation happens, right? Or the rotation, generalized rotation happens. That must correspond to the unit of a conjugate operator to this. Consider this quantity, e to the minus I p operator x by h bar. Ask yourself, what was this x? This x is an amount by which something got translated. But it also corresponds to the eigenvalue of x operator. And if you remember, x operator and p operator have this funny commutator, the Heisenberg uncertainty principle. Okay? So the way to form such operators is look for the conjugate operator to the Hermitian that you started with. Let's say I give you some guy. Look at the guy conjugate to it, which is related to it through some h bar. Okay, at the commutator level. Its eigenvalue like quantity will be sitting in the exponential, and the entire thing will be divided by h bar. That is the simple way by which you can always guess what the correct unitary operator looks like. Okay. Another way to put it is that this entire thing is unitless. This has no units. It has no dimension. So if I give you some operator, it has dimensions. You've got to cancel out those dimensions with h bar. So that's how you will identify what's sitting here. Okay. So these objects are always expressions. These unitary transformations are again an outcome of the Heisenberg uncertainty principle, if you wish. Good. So note, when I write down u theta as e to the minus I lambda theta, u dagger is just that minus I becomes plus I. Okay? Such that u dagger u must equal to 1. Now, if theta acts on psi and this operator and gives me the eigenvalue theta, then u theta acting on psi, we discussed this before, it's e to the minus I lambda theta operator acting on psi. This will just pull out these eigenvalues. These are just phases. So this is how we know how much we're rotating by. When I act with this unitary transformation, how much am I rotating in the same term? A phase comes out. Okay. Now, there is one very important relation that will be very useful to us going forward from here. Suppose I give you two Hermitian operators, theta and a. No, two Hermitian operators, theta and a. Suppose I say, okay, so there's the unitary operator u of theta, which is written as e to the minus I lambda theta. Then there's this famous relation which goes by the name of three mathematicians, Baker, Campbell, and Hausdorff, which says that if I take this operator a in the middle, put it in the middle, and if I have u theta to its right and if I have u theta dagger to the left, then this object, which can be written more simply as this, a in the middle, e to the minus I lambda theta on the right, e to the I lambda theta on the left. If I have such an object, then this entire huge thing is obtained. At first sight, you might say, why do I care? Well, you'll see very soon why this is important. Okay? If not today, then within a class, we will see why this is important. But note what's coming out here. What we're saying here is that if I take some operator A, put in a unitary transformation to its right, and put the opposite of that unitary transformation on the left. Okay? How does this operator itself look like, this new guy? So I had the original operator, now I put in transformations on both sides. What does this operator now change into? And what you see is that it can potentially change into something pretty weird. Why? It's not just the operator itself. That's just the first term. There are actually a huge number of other objects that are also coming out. Let's look at the second term. The second term involves a commutator of theta with a. The Hermitian operator theta that is causing the transformation with that operator. Okay? And by how much? Lambda. Alright? And look at the next term. The next term is yet more complicated. It's a nested commutator. So there's first a commutator theta with a, and whatever comes out of that, remember I told you that in general, a commutator of two operators leads to an operator. So this guy again will have to go back into a commutator with theta again. And what's the weight factor? Lambda square. In fact, it's I times lambda square by 2 factorial. Does this expansion remind you of some other expansions you might have seen? Very good. And you can see that even the nth term, look at what the nth term looks like. It's hideous. Each term is getting more and more complicated. These commutators are getting more and more nested. At the heart of that nth term is theta of a. But then whatever comes out of that, I put it back into another commutator. And I keep doing this n times. At first sight, this just looks like madness has broken up. Because it's never going to end. Careful. Your commutator might come to a brutal end. Unlike this thing, your spine could, right, snap. So be careful where you sit. So there's one special case that applies to all of this. So yeah, this is messy. Yeah.
So say the operator A is Hamilton.
Yes.
And theta is say operator that commutes with the Hamilton.
That's what. So we're coming to that. So if we look at the general case where theta and A commute, for instance, in your case, let's say the Hamiltonian, and let's take the momentum operator for the free particle. They commute. So in that case, all these commutators will identically vanish. The first one automatically vanishes, so that term goes. Now look at the second one. The heart of it, that is the first commutator, that will give you 0. But then the next commutator is theta with 0, which is 0. So in that way, every such nested commutator also vanishes. Because at its heart, the first result will always be a 0. And then that kills every other commutator in the nest. Okay? So for the case where theta and A commute with one another, which basically means that those two operators share the same eigenbasis, in that case, and that case alone, only the first term remains. And what does that mean? It means that if I try to transform the operator with these transformation functions on the two sides, u theta and u theta dagger, it just gives you back the same guy. It doesn't change. It doesn't rotate. Why? How do you physically justify this? This rotation has no action because the eigenstates, they share the same eigenstates. So it just continues to stay in that same line. There's no need to rotate. You're trying to rotate, it's just meaningless. Okay? That's what this means. Now, if I have an operator A, what is this guy telling us? This relation. So let me spell that out a little more clearly. What it's telling us is the following. That if I have an operator A which acts on its eigenstates, this eigenstate given by this complete set, okay, then I guarantee to you, yeah.
So is the creation of a unitary operator always
if that operator, the original Hermitian operator, is analytic, always possible to get the unit. If the original operator has some sickness in it, this might cause an obstruction with the creation of the unitary operator. But if the operator is analytic, shouldn't be an issue. Okay. So my claim is that this, yeah.
If the commutator of A and theta is non-zero,
Yeah.
but what this u dagger AU means is to rotate and rotate it back. But would it be different if the commutator is not?
Yeah, because it's not just giving you back that operator A, no, you will get all these other possible terms. It means that when you're carrying out that transformation, you're not coming back to the guy you started with. You started with the operator A. Now you'll have that A plus many other guys. Potentially an infinite number of terms. Potentially.
But the action of u is just to rotate.
Yes.
And u dagger is.
But the operator, this operator A is also having to rotate along with it. Because when you're changing the states, these operators must also transform. That's what this guy is saying. For the special case where they don't transform, well, this is telling us that if A acts on its eigenbasis, then there also must exist another operator B, which is defined in this fashion. Okay, U, A, U theta dagger, alright? Such that if B acts on its eigenbasis as well, what is that eigenbasis? It's the rotated one. A's eigenbasis but rotated. Then the eigenvalues do not change. So my claim is that the eigenvalues, so if this rotation remains leaves the operator invariant, then the eigenvalues also remain invariant. That's what this is telling us. Now it looks sensible, but we should check this out. Okay? Because what I'm trying to say is that if those commutators all go to 0, what we've shown is that the transformation leaves an operator invariant. The operator doesn't change. If the operator doesn't change, then surely its eigenvalues also shouldn't change. That's logical. How do we check this? Okay, so this is the eigenvalue equation. A acting on its eigenbasis gives you an eigenvalue. Act with the unitary on both sides, okay, and purposely sandwich in between that operator A and the ket, put in a complete set of states, which here just the identity is just u dagger u. Here you don't need to sum over anything because u dagger u is equal to the identity. So you just place this u dagger u in the middle. क्या किसका मोबाइल बज रहा है यार? So if I place that u dagger u in the middle, okay. Now here I just flip these two. Why was I allowed to flip these two? Sorry, one is an eigenvalue. It's just a number. I should be able to flip it to the operator. So good. So that gives me this. Now look at this. This term here, u dagger, that's just the B operator. This u theta acting on A is just the B ket, the rotated ket, and this u theta acting on this is just the rotated ket. So this guarantees to you that if I started with this A being the eigenvalue of the old operator, the new operators have the same eigenvalue A. That's what this is telling us. Okay. So it restores sanity if you wish. That if the rotations didn't change the operators, they cannot change the eigenvalues. There's nothing very shocking about that. Good. So in that case, what we say, we have a language for this. If the eigenvalues are unchanged under the transformations, under these rotations, we say that the operators A and B, B being u, A, u dagger, we call them unitarily equivalent observables with identical spectra. That's a mouthful. Think about that. We call them unitarily equivalent observables. So if the operator A was some observable, some experimental measurable, we say that B, which is the rotated version of this, is unitarily equivalent to that old observable. Why? Because the spectra, the eigenvalues of A, are still the eigenvalues of this rotated object. Okay? They have matching eigenvalues. Alright? Good. Alright, enough for today.